Good morning, all. Today, we will be learning about full wave rectifier. In the last class, I think you remember we have studied about half wave rectifier, which was an important topic. Similarly, this is also an important topic, full wave rectifier. Now, full wave rectifier is actually a combination of two half wave rectifier circuits which are connected, that one of the circuit is operative during first half cycle of the input and the other is operative during second half cycle. So this will be clear. This is a figure given below. Here you can see two circuits. This is one and the one two. Okay. Now they say that this is actually a combination of two half-wave rectifiers, and this first circuit becomes operative during first half cycle of input AC voltage, and the second circuit becomes operative during the second half cycle of input AC voltage. So I'll repeat. This is actually a combination of a two half-wave rectifiers with one circuit operative during the first half cycle of input AC voltage, and the second circuit becomes operative during second half cycle of input AC voltage. Now this is the output waveform. The input waveform will be a sinusoidal wave, and this is the output. See, here you are getting a continuous output, whereas in full half wave rectifier you are getting a pulsating output. Now let us see how this continuous output is obtained. Here you use a center tap transformer. That is, the secondary of the transformer is center tap. That's why it is called center tap full wave rectifier. Now we'll go into the theory, that is the working. So I will brief this paragraph. You can go through it later. See, during the first half cycle of input AC voltage, what happens is that the diode D1, it will get forward biased, so that will conduct, whereas diode D2 will get reverse biased, that is, it will not conduct. So since the D1 conducts, a current flow occurs through RL in the direction from A, D1, C, D, O. So you will get a corresponding peak in the output, that is, current flow is there. Okay. So the first peak is actually current flow due to D1. Now during the second half cycle, what happens is that just reverse occurs, that is, D1 will get reverse biased, that is, it will not conduct, whereas D2 will get forward biased and it will conduct. So current flow occurs. Why? Because D2 conducts, and so the current flow direction will be from B, D to B, D to E, D, O. Okay, so the only thing is that during first half cycle, D1 forward biased, so it will conduct, whereas D2 does not conduct. Why? Because it will be forward biased. So current flow occurs in the output due to D1 and in the direction A, C, D, O. That is, you get a peak here. See here, this one. Okay. Now during second half cycle, what happens is that D1 will get reverse biased, so it will not conduct, but D2 will get forward biased and it will conduct. So again current flow occurs in the direction B, D2, E, D, O. That is this particular peak. And again when another half cycle comes, D1 will get forward biased, and this continues. So first half D1 forward biased, D2 reverse bias. In the second half, just the reverse. So this particular cycle repeats. As a result, you will get a continuous output in the continuous waveform in the output. Okay, so that is described here. So you can go through this paragraph. Now here the PIV, and we have already told in the last class, it is a peak inverse voltage or the maximum reverse voltage that can be applied to the diode without damaging the junction. In this case, PIV is about twice VM. VM is maximum secondary voltage or maximum voltage across the half secondary winding. Whereas in half wave rectifier it was only VM, but in full wave rectifier it is twice VM. Now efficiency, these are all we have already learned, just only a few variations. Efficiency is equal to DC power output by AC power input. DC power output is I square DC RL, whereas AC power input is I square RMS RF plus RL, where RL is a load resistance and RF is the small RF is the resistance of the diode. Now the peak value or the maximum value of load current IM is given by VM. VM is maximum secondary voltage divided by RF plus RL. Okay. Now we have to calculate average current or IDC. It is written like this, that is integral from 0 to T by 2 I dt. I is the instantaneous value of current divided by 0 to T by 2 dt. I am not explaining it because this I have already explained in the case of half wave rectifier. So if you don't remember, please go through it. Okay. Now this derivation part is not given in your text, but I have derived it for you. So I think it's better you take a notebook and write the full derivation, because derivation is very important for your exams. You have to derive it completely. Okay, so this is IDC. We are going to calculate the expression for IDC. Here you are only integrating from 0 to t by 2. Okay, in the case, just compare it and study half-wave rectifier and full-wave rectifier. Then you will understand the minor differences that occurs between these two rectifiers. Okay, here we are integrating between the limit 0 to t by 2 I dt divided by 0 to t by 2 dt. So integral dt is t. On applying the limit in the denominator, you get t by 2. But when it goes to the numerator, it will become 2 by t. Okay, so 2 by t integral 0 to t by 2 I dt. 2 by 2 is kept as such, and in place of I we write Vm sin omega t by Rf plus RL. Vm is taken outside, Rf plus RL is also taken outside. The only thing is remaining is integrating part, remaining is sin omega t. Integral sin omega t is minus cos omega t by omega. So that is written here. Then what else? This omega is taken outside and you are left with the what? Cos omega t. So in place of t you are applying the limit. So cos omega capital T by 2 minus the other limit cos 0. Then this is the same. Then cos omega, in place of omega you write 2 pi by t, because t is equal to 2 pi by omega. Then t by 2 as such cos 0. Then this on simplifying you get minus 1. You will get it as cos pi. Cos pi is minus 1. And cos 0 is also 1. Then this is written like that. Then on simplifying you get this minus 1 will be minus 2. So minus 2 and minus 2 will be 4. Vm t as such, Rf plus RL is also kept as such, and here omega again it is replaced by 2 pi by t. Okay, t and t get cancelled, so you are left with 2 Vm by pi Rf plus RL, and this Vm by pi Rf plus RL is replaced by the term Im. Okay, so the expression for IDC is 2 Im by pi. So if once IDC is known, you can calculate PDC. What is PDC? I square DC RL. You got IDC as 2 Im by pi. So that's square RL. So this is the final expression for PDC. Now we will find the expression for PAC. So in order to find that, first of all we have to find an expression for IRMS. Okay, now we know I square RMS as already told in half-wave rectifier. Here the limit is 0 to t by 2 I square dt by 0 to t by 2 dt. Then this is this part will be t by 2. So on taking to numerator will become 2 by t. 0 to t by 2. I is taken as Im sin omega t. So I square will be Im square sin square omega t. Now Im square is taken outside. Now you are left with sin square omega t. We know sin square theta is 1 minus cos 2 theta by 2. On applying that mathematical expression, you will get 0 to t by 2, 1 minus cos 2 omega t by 2. Okay. Now 2 Im square is kept as such. Now this denominator 2 is taken outside. Then 0 to t by 2. Here there is a 1, okay. It's not clear. 0 to t by 2, 1 minus cos 2 omega t dt. Then the 2 and 2 get cancelled. The next step will be Im square by t. Then you are splitting that integral part, that is from 0 to t by 2 dt minus 0 to t by 2 cos 2 omega t dt. Okay, then again you are going to write Im square by t is kept as such. Integral will be t, and integral of cos 2 omega t, it will be sin 2 omega t by omega t. Then limit is 0 to t by 2. Now in the next steps we are going to apply the limit. Okay, Im square by t, then t in place of t by 2, then sin 2 omega, omega is replaced by 2 pi by t, and in place of small t we are replacing it with the limit t by 2. Then omega is again replaced by 2 pi by t, and here in the place of small t you are applying t by 2. Now this on simplification you get Im square by t, t by 2 is kept as such, and this particular part will get 0. So the final expression for I square RMS is Im square by 2. So then what will be IRMS? It will be Im by root 2. Okay, then PAC will be, from once IRMS is known, we can calculate PAC. What is the expression for PAC? I square RMS RF plus RL. which is already told while discussing half-wave rectifier. So in place of I square RMS, we can write the derived one, that is Im square by 2, and then into Rf plus RL. So now you got the expression for PDC and PAC. Then definitely you can calculate the expression for efficiency. What is efficiency? PDC by PAC. So here this is PDC, the expression that we have derived now, and this is the expression for PAC which we have derived now. On simplification, you get this particular step. Eta is equal to 8 by pi square RL by RF plus RL. 8 by pi square is 0.81 into RL by RF plus RL. Now dividing throughout by RL, we get eta is equal to 0.812 divided by 1 plus RF by RL. Now if RF is very small compared to RL, the efficiency will be maximum, and that will be 0.812. This means that 81.2% of AC power is converted into DC power. In other words, full wave rectifier is twice as effective as half wave rectifier. So in full wave rectifier, efficiency is high when compared with half wave rectifier. That is about twice as effective as half wave rectifier. In case of half wave rectifier, I think it was about 0.4 something, right? Now here it is just twice, about 0.8. So it is more, it is twice as effective as half wave rectifier. Now we will calculate the ripple factor, which we have already derived in the case of half wave rectifier. So now I am not elaborating it. In the expression is gamma is equal to root of IRMS by IDC the whole square minus 1. And now you substitute the values of IRMS and IDC that we have just obtained, and you get the gamma or ripple factor as 0.48. So in half wave full wave rectifier, DC component is more than AC component, hence widely used for rectification when compared to half wave rectifiers. In case of half wave rectifier, the ripple factor gamma that you obtained was 1.21, that is greater than 1, but whereas in the case of full wave rectifier, it is less than 1, that is it is just 0.48. This means that AC component is less in full wave rectifier, that is DC component is more in full wave rectifier, which is very effective, that is ripple factor is less than 1, so its efficiency is also high. So full wave rectifier ripple factor is less and efficiency is also high in the case of full wave rectifier. So full wave rectifier is widely used for rectification, that is they are more commonly used for rectification when compared with the half wave rectifiers. Now these are just the disadvantages. It is very difficult to locate the center tap on the secondary winding. DC output is small and the diode must have a peak inverse voltage of twice VA. Okay, so when you study this, just compare between half wave and full wave rectifier, because you can expect a question either from half wave rectifier or full wave rectifier. That is to discuss the working of a half wave or full wave rectifier with the circuit diagram, input and output waveforms, then the working, and they may also ask you to derive the expression for efficiency. That is, in that case, you have to show the full derivation. That is, first of all, you have to derive the IDC, then PDC, then I square RMS. I mean, from that we get IRMS, and then we'll have to calculate PAC, and then we have to obtain the final expression for efficiency. So study this. When you study this, just compare and study. Okay. So full wave rectifier is widely used for rectification when compared with half wave rectifiers. Okay. So study this carefully. I will upload this note. I will upload this note also along with this video. Okay. Thank you.